Stoichiometry involving gases. Okay, in the old days, um, we had one way to get to moles, right? If I knew the mass, if I knew how many grams of reactant A I had, I could use the molar mass of reactant A to convert to moles, and then I could use the coefficients of the balanced equation to convert to moles of product, and then use the molar mass to get back to grams. Well, we got a new way to get to moles now, right? Using PV is equal to nRT. If I knew the pressure of a gas, the volume of a gas, and the temperature of the gas, I can use the gas constant to convert to moles and then convert from moles of reactant to moles of product and to whatever I want. Grams, liters. Nitrogen and hydrogen react to form ammonia gas as follows. At a certain temperature and pressure, I guess they're constant. 1.2 liters of nitrogen reacts with 3.6 liters of hydrogen. If all the nitrogen and the hydrogen are consumed, what volume of ammonia at the same temperature and pressure will be produced? Okay, so this looks like a case of Avogadro's law, right? As long as the temperature and the pressure is constant, I can treat liters of gas like moles of gas. So I can talk about 1.2 liters reacting with 3.6 liters. Well, for every 1 liter of nitrogen, I need 3 liters of hydrogen. So these are going to burn out together. For every 1.2 or 3.6 liters of hydrogen, according to the equation, for every 3 liters of hydrogen, you make 2 liters of ammonia. All right, so this is what Avogadro's law gives us the power to do. Treat the coefficients in the balanced equation like volumes, because moles and volume are directly proportional. So as long as I have a temperature and a pressure that are constant, I can do this. I can treat moles of gas like liters of gas. And treat the coefficients as though they are liters. All right, so that's one kind of problem. Calculate the volume of nitrogen gas generated at 21 degrees Celsius, 823 millimeters of mercury, upon the decomposition of 60 grams of sodium azide. All right, so they gave me grams of sodium azide, so I can use the molar mass of sodium azide to convert to moles. I can use the coefficients in the balanced equation to convert from moles of sodium azide to moles of nitrogen. Now that I have moles of nitrogen, I have a temperature and a pressure, and I can plug into PV is equal to nRT and solve for what do they want? The volume. Make sure that the pressure is in atmospheres, moles is moles. Make sure the temperature is in Kelvin. And I can plug into PV is equal to nRT and solve for that volume. So, you know, it's an old problem with a new twist, right? We just have to get to moles of what we want, and then we can use PV is equal to nRT to get the unit we want, liters in this case. Another fact about gases, all right? So we've got Avogadro's fact, we've got Dalton's fact, we've got Charles's fact. This is Dalton's law of partial pressures, which says that the total pressure of a mixture of gases can be treated as the sum of the partial pressures, all right? So since gases mix evenly and no gas is different than another, if we're treating gases in an ideal way, the pressure of one gas plus the pressure of another gas plus the pressure of a third gas will add up to be the total pressure in the container. So as long as that's true, as long as the temperature and the volume are constant, I can treat moles of gas like pressures of gas. So again, all gases are the same. If they're all spread out, it doesn't matter what kind of gas it is, right? How big the molecule. They're all small compared to the container that they're in. So I can treat moles of gas like pressures of gas. They'll all exert the same pressure, regardless of the type of gas. So a reaction shown is carried out at a constant temperature and a constant volume. At the start of the reaction, the vessel contains only dinitrogen tetrahydride and oxygen, each contributing a partial pressure of 2 atmospheres. Okay, so we're looking back at this, right? all right, this reaction is allowed to go forward until 50% of the reactants are consumed. What is the total pressure in the container at this time? So just taking a step back again, as long as the temperature and the volume are constant, I can treat pressures of gas now like moles of gas. So just like I did in this problem where I treated volumes of gas like moles of gas, I can now do the same with pressures. So if I'm starting with 2 atmospheres of each of these gases, and it's allowed to go 50% forward, I'm not using up those 2 atmospheres of gas, right? For every 1 mole of, or 1 atmosphere of hydrogen, you're making 1 atmosphere of nitrogen and 2 atmospheres of water. So I'm only using up half the oxygen. So the total pressure in the container would be the sum of the pressures, right? They're all in the container. So 1 atmosphere of the leftover dinitrogen tetrahydride, 1 atmosphere of leftover oxygen, plus the atmosphere of the products I produced. So the total pressure in the container is going to be 5 atmospheres. Again, another look at this, right? They're in the container. So here's my container. I'm putting the reactants in. This is only allowed to go 50% forward, so I'm not using up all of my reactants. So according to the coefficients, for every 1 oxygen, you're making 1 nitrogen and 2 waters. So ready, set, boom. I've made the amount of nitrogen and water I'm going to make. So how many particles do you have in the container at this point? 1, 2, 3, 4, 5. All right, and that's what's exerting the pressure inside the container, the leftover reactants and the products.